Hello everyone, welcome back to this video where I'm going to be talking to you about using the eigenvalue method to find the solution to the given differential equation. And then we're going to use a computer system or graphing calculator to construct a direction field and typical solution curve for the given system. So first of all, we have to know that the x prime is basically equal to x1 prime over and x2 prime. It can be expressed in this matrix form. And also, from here, we have to know that x prime can be expressed as some matrix A multiplied by the matrix of x. In this case, the x matrix is equal to x1, x2. So we can thus write this whole differential equation here with x2 prime and x1 prime as simply x1 prime, x2 prime is equal to A, and the matrix A is simply the coefficients of these two matrices. So 3 from over here, 5, and then on the bottom row, 4 and -1. So 3, -5, oops, -5, 4, and -1. And this matrix is multiplied by the x1, x2 matrix. Now, the eigenvalue method requires us to first find the eigenvalues and then the eigenvectors. So basically, the eigenvalues will give us the coefficients of each of these t exponents here, while the eigenvectors will give us what goes in here. The eigenvalues are represented by the Greek character lambda, which is this form over here. And in order to find the eigenvalues, we have to take the determinant of A minus lambda times the identity matrix. And the determinant is always equal to 0. So here, our A matrix is this matrix over here. And remember that our identity matrix is going to be equal to 1, 0, 0, 1. So basically, the determinant is thus equal to, first we have to calculate A minus lambda I. So we have basically 3, -5, 4, -1, minus lambda times identity matrix 1, 0, 0, 1. So lambda times this matrix is simply equal to lambda 0 and 0 lambda. So we'll plug that in there. So then this will become 3, -5, 4, -1, minus lambda 0 and 0 lambda. And remember that this will be equal to 0. So we can thus write it as, in one matrix as 3 minus lambda, -5, 4, and -1 minus lambda. Um, oh wait, and sorry. This one does not equal 0. Rather, the determinant of it equals 0. So we have to make sure not to get that confused. So basically, to take the determinant of this matrix, it's more commonly written in this form. And the determinant is um, this multiplied by this minus the product of these two. So it's always the product of these two values in the matrix minus the product of these two values for a 2 by 2 matrix at least. A 3 by 3 matrix is slightly more complicated but follows the same general idea. So then 3 minus lambda times -1 minus lambda minus 4 times -5 is equal to 0. And we can distribute this out as -3 minus 3 lambda plus lambda plus lambda squared plus 20 is equal to 0. Simplifying this, we get that lambda squared minus 2 lambda plus 17 is equal to 0. Now, this is a form that where we would need to apply our quadratic formula, which is given by, in this case, lambda equals -2. Oops. Well, first let's write the quadratic formula more explicitly. So the quadratic formula says that x equals -b plus or minus square root of b squared minus 4ac over 2a. So this is our a coefficient, this is our b coefficient, and this is our c value. So in this case, we can say that lambda, in this case, equal to x, is equal to -2, which is 2, plus or minus square root of -2 squared, which is 4, minus 4 times 1 times 17 over 2 times 1. And this gives that lambda 1 equals equals 2 plus 8i over 2. We get an imaginary number over here because the value inside the square root is negative, which simplifies to 1 plus 4i, and a lambda 2 value of 2 minus 8i over 2, which simplifies to 1 minus 4i, as we see over here. Now, our next step is to find the eigenvectors. So to do that, we will note that the eigenvector equation is a minus lambda I times the eigenvector is equal to 0. And thus, our eigenvector v has to satisfy this equation, but it cannot be 0. It must be non-zero. And we will substitute our value for lambda into this equation. And unlike what we would do for non-imaginary valued equations, for imaginary value equations, we only need to substitute one of the lambdas because these lambdas are conjugates of each other. So we only need to consider one of the lambda. So we can either substitute lambda 1 or lambda 2 into this equation. So I'm going to pick a lambda 1. So A minus lambda 1 times the identity matrix will be equal to 3, -5, 4, -1, minus a lambda, which is 1 plus 4i. So 1 plus 4i times the identity matrix, which is equal to 1, 0, 0, 1. And then all this multiplied by v should give us 0. And the 0 here, it's worth noting that it's the 0 matrix. So basically, in this entry, there are two values, 0 and 0. And our v here is also a vector, technically represented as such. And it has two components since this is a two-dimensional problem, a 2 by 2 matrix problem. So it has v1 and v2. So just keep this in mind as we do this problem. So simplifying the expression inside the parentheses, we have that this matrix equals 3 minus 1, which is 2, minus 4i, -5 minus 0, which is -5, 4 minus 1, which is 3, and then minus 4i, and then -1 minus, oh wait, sorry. This value is meant to go to the right. And over here we have 4 minus 0, which is equal to simply 4. And then the other one we have -1 minus 1, which is -2 minus 4i. So what we're doing here is we're simply like multiplying this by each entry in our matrix. And this matrix multiplied by v will give us the 0 matrix. So in order to solve this problem, we can write our augmented matrix. So our augmented matrix in this scenario will be written as 2 minus 4i, -5, 0, and 4, -2 minus 4i, 0. And we would row reduce this matrix in order to get our final values, or alternatively, we could have used a system of equations directly to solve for v1 and v2. Because remember that v1 is v is equal to v1, v2. So now we're going to be performing a row reduction on this matrix. So the first step to do is to divide row 1 by divide row 1 by 2 minus 4i. And the next step after doing that is to After that we have 1, so after that we multiply row 1 by -4 and add it to row 3. So let's carry that out. So dividing row 1 by 2 minus 4i, we get 1, and -5 over 2 minus 4i, 4 -2 minus 4i. Now multiplying row 1 by -4 and adding it to row 3 gives us 1 -5 over 2 minus 4i, 0, um, so, and, first, before we multiply this one by -4, let's simplify it a little bit. So, -5 over 2 minus 4i can be simplified by multiplying it by the conjugate, which is 2 plus 4i over 2 plus 4i. So multiplying it by the conjugate, we would have -10 minus 20i over 4 minus 16 I squared, and I squared is equal to -1. So we would thus end up with -10 plus 20i, and we change this to plus because when we write the negative sign outside the fraction, we are indirectly putting a parentheses around this term over here and distributing the negative sign inwards. Over 4 plus 16, which is 20. So this simplifies to negative 1/2 minus I. So -1/2 minus I is equal to this entry over here. So we can replace this entry by -1/2 minus I. So now our multiplication becomes a lot simpler. When multiplying negative row 1 by -4, we get simply that we have, and adding it to row 3, we get simply -4 times -1/2, which is 2, and then -4 times -I, which is equal to 4i. And then -2 minus 4i, which makes this last row equal to simply 0. And sorry, I forgot to add a row over here. Because we cannot forget our 0 values because they're important in our augmented matrix. So don't forget that we have 0 terms on this side of the matrix. And also over here. But rewriting it in terms of our original matrix V, we can note that this means that 1 -1/2 minus I 0 0 times V1 V2 is equal to our matrix 0, 0. And thus now we can solve nicely for V1 and V2. Now we can um, multiply our matrix over here to find that um, V1 V1 plus negative 1/2 minus I times V2 um, is equal to 0. So that will give us our first row. So multiplying it by V1 and then V2, and it's equal to this first term of 0. And then the second 0 will come from 0 times V1 plus 0 times V2, which is obviously equal to 0. So because 0 plus 0 is equal to 0. And this gives us the relation that V1 is equal to 1/2 plus I V2. Because negative 1/2 minus I is equal to negative 1/2 plus I. So then, so this simply means that the vector V, which is expressed as V1 over V1 V2 is equal to, and we can pick any value for V1 and V2, 1, 2, 3, or like any decimal 0 0.5, 0 0.333, even pi. So we have infinitely many solutions, but this simply gives us the relationship between V1 and V2. So the simplest one is to pick V1 is equal to, or rather V2 is equal to 1, and thus V1 will be equal to 1/2 plus I. So this is equal to our V1. And in this case, since we have a complex value solution, and first of all, we have to note that V1 over here is different than the V1 over here. The V1 over here denotes the first eigenvector. And usually when we have two different eigenvalues, we have two different eigenvectors. But in the case of a complex solution, it is a little different since we only have to consider one of the eigenvalues, and thus we will only have one corresponding eigenvector. However, that eigenvector will be kind of applicable to both C1 and C2. Or I guess not really because the the fact of the matter is that we'll have an imaginary part and a real part. So we'll break those two up, and this one will be our imaginary part, I believe, and then this one will be from our real part. So how do we break this up into imaginary and real parts? So first we have to come up with our xt solution as of now. So as of now, our xt solution is equal to 1/2 plus I 1 e to the negative 1 plus 4I t. So we have to separate this into real and imaginary. And to do this, we will use Euler's expression. So Euler's formula is the following. E to the negative ik, or rather e to the I kt is equal to cosine kt plus I sine kt. And so taking our solution here as breaking this up using Euler's formula, we will have that e to the negative 1 plus 4I t multiplied by 1/2 plus I 1 is equal to, and here we want to factor out e to the power of t. So e to the power of t times 1/2 e to the um 1/2 e to the, or rather factor out e to the negative t over here, and then we will have 1/2 e to the negative 4it. And on the plus I times e to the negative 4it. And on the denominator, we will have simply e to the negative 4it. And why is this? Well, it is because of how exponents work. So when we say e to the power of negative 1 plus 4I times t, we're actually saying e to the negative t times e to the negative 4it. Because we add the exponents, that is the exponent rule. So here we're just breaking it up by factoring out an e to the power of negative t. So we usually factor out e to the power of t, but sometimes we also factor out e to the power of negative t, or some other scalar multiple of t can also work, I think. So over here then we would be left with applying our Euler's formula to these portions. So it'll be equal to e to the power of negative t, and inside the matrix we'll have 1/2 times, so using apply Euler's formula for e to the negative 4it, we will have that k is equal to negative 4. So we will have 1/2 times cosine of negative 4t plus I sine of negative 4t. And then the second part will just be I times cosine negative 4t plus I sine negative 4t again. And we can definitely simplify this later. And on the lower side of the matrix, we will have cosine negative 4t plus I sine negative 4t. So now simplifying this further, we have e to the power of negative t time and inside the matrix 1/2 cosine negative 4t plus I sine negative 4t, and then distribute the I inside the parentheses, so plus I cosine negative 4t, and then I times I is I squared, which is negative 1, so negative sine negative 4t. And on the bottom we have cosine negative 4t plus I sine negative 4t. Now, then the last step is to divide this into our imaginary and real parts. And sorry, going back to this part where we found our eigenvector, it is worth noting that the eigenvalue and eigenvector pairs, we will have two pairs and they will be 1 plus 4i 1/2 plus I 1 and 1 minus 4i 1/2 plus I 1. And in addition, the generic formula for the x vector with the whole matrix broken down into imaginary and real parts is x equals c1, the real part, times e to the eigenvector that we chose, which is 1 plus 4i t times the eigenvector we found, which is 1/2 plus I 1 plus C2, the imaginary part, e to the 1 plus 4i, which is again the eigenvector we chose, times 1 over 2 plus I 1. So what the real here is real and imaginary parts mean is that over here we want to include only the real parts. So cosine of negative 4t and negative sine of negative 4t. But we exclude these two values from the real part since they are imaginary parts. However, in the imaginary part, we will have basically sine of negative 4t and cosine of negative 4t. So x is thus equal to c1 e to the 1 plus 4i, or wait, sorry, we already divided it up. So e to the negative t times what goes in the vector is 1/2 times cosine of negative 4t, which is part of the real part. And then negative sine negative 4t. And then on the bottom, it will be the real part corresponding to the bottom part, which is cosine negative 4t. And plus c2 e to the negative t. And the e to the negative t is from here. And then the parts corresponding to the imaginary parts. So we have sine negative 4t plus cosine negative 4t over sine negative 4t. So sorry about something. I just noticed the mistake I made since I was checking and it didn't match the answer over here. So where I went wrong was that over here somehow a negative sign suddenly appeared out of nowhere. So I think that was just a mistake on my part. And so we're gonna go ahead and erase it. So certain things will definitely change. So let's just go ahead and remove it. So we won't have to factor out a negative t. It will just be t. And then this one will be simply positive 4it, positive 4it, positive 4it. And it will simply be e to the power of t. And we will remove all the negative signs in front of the 4. Like so. And this one should match our given answer now. Which is going to be equal to everything the same except with positive 4s and positive t's. So let's see if it matches our form now. Yep, it certainly does. So we know that we have correctly solved this problem. And wait, actually there's one thing is that there's supposed to be 1/2 in front of this cosine 4t. So where did that come from? Oh, sorry, the 1/4 comes from forgetting to distribute this into the parentheses. So we have 1/2 over there. So 1/2. And now this matches our answer perfectly. Okay, cool. Now we can go on to our last step, which is to choose the correct graph from below. And Before using any graphing software, I'm first going to mention how we can approximate what the graph will look like just by using these eigenvalues. So these eigenvalues are basically complex conjugates. So the eigenvalue 1 and 2 is equal to 1 plus or minus 4i. So they are complex conjugates. And if we look at our if we look at our rules for how to draw phase portraits, phase portraits, um, complex conjugates give us a spiral, as seen over here. As seen over here, a Google search of the phase portrait of a complex conjugate shows that it simply gives us a spiral. However, we want to know whether it's spiraling in or spiraling out. So how would we determine that? We would have to go back to our matrix. And we see here that when lambda 1 and lambda 2 are complex conjugates with a non-zero real part, as is our case, we have a spiral. So we get cosine and sine graphs. We get cosine and sine in our equations, and that's why we have a spiral. But how do you know whether it spirals in or out? We do this by looking at the eigenvector. Not the eigenvector, but the eigenvalue. If the eigenvalue is positive, as in this case, it will spiral outwards, as seen in D. And as you see, the arrows are all pointing outwards. And if the eigenvalue is negative, it will spiral inwards. So let's say we had an eigenvalue of -1, then we would get a spiraling inwards graph. However, we don't know whether it is spiraling outwards clockwise or counterclockwise because it can be going in this direction or in that direction. So how do we tell? We can multiply. We can check certain points by using the A matrix, which was 3, -5, 4, -1, and pick a random point in the XY system. Let's pick 1, 0 because it's just such an easy point, and 1, 0 on the XY Cartesian coordinate will be equal to 1 and then 0. So it'll be this point over here. And when we multiply these two matrix together, we get 3, because 3 times 1 is 3, minus 5 times 0, which is 0. And we have 4 times 1, which is 4, minus 1 times 0, which is 0. So we have 3, 4. So we thus, sorry, not 3 over 4, but 3, 4. So we know that the vector at 1, 0 is going basically 3 units to the right and 4 units up. So about this way. If this isn't enough information to tell you whether it's spiraling counterclockwise or clockwise, you can test another point. For instance, you can test Let me see, what is a good point to test? Uh, Actually, this alone should be enough to tell you that it's rotating counterclockwise because we can never have a clockwise rotation that has an arrow pointing that way. So we know that it's going counterclockwise, which is matched by D, and spiraling outwards. And because it is spiraling outwards, the origin is classified as an unstable. However, if this was spiraling inwards, the origin would have been stable. So just keep those facts in mind. And I hope this video helped you, and we'll see you in the next video.